Second lecture of beta decay. So today we are going to study what is energy spectrum of beta particles. So when we plot a graph of number of beta particles against kinetic energy of the beta particles, then whatever graph we get, that is we call as energy spectrum. So here you can say that we have plotted energy on the x-axis and number of beta particles on the y-axis. Now, what is continuous beta ray spectrum? So, as the energy distribution of the emitted particles is continuous in the sense energy can take any value from 0 to maximum. The spectrum which we get, that spectrum also we call it as a continuous spectrum. So, when we talk about a continuous spectrum, every continuous spectrum has a definite maximum. So, here you can see that this is the maximum. Okay, so every continuous spectrum has a definite maximum, the height and position of which depends on the nucleus emitting the particle. There is also a definite upper limit or end point energy E of for the particles emitted by the nuclide. So here this value, it is the end point energy. This endpoint energy is different for different nuclides. So these properties of continuous spectra are observed for both natural as well as artificial beta emitters, and when the emitted particles are electrons or positrons. Now, what is single and complex spectrum? So in some cases of beta emission, single continuous spectrum is found which has a single endpoint energy. So when we get a single continuous spectrum with single endpoint energy, such a spectrum is called as single. Now, when there are two or more spectra with different endpoint energies and intensities, then the spectrum is complex. So many beta emitters, basically they have complex spectra where you will have two or more continuous spectra with different endpoint energies. So you can have a look at this graph. Here you can see this is one graph, this is another simple spectrum, this is third simple spectrum. So here you have three simple spectra with three different endpoint energies. This is one endpoint energy, second, and here you can see the third one, right? Okay, so now let us talk about what is average energy of beta particles. Now this spectra, we are getting three spectra. So this spectra can be separated by analyzing the curves obtained with a magnetic spectrometer. The average energy of the beta particles which form the continuous spectrum can be calculated from the energy distribution curve. So the total energy is found by integrating the product of the number of particles with a given energy and that energy. The number of particles is found by integrating the number of particles with a given energy with respect to the energy. This number is just nothing but the area under the distribution curve. So the average energy is number of particles. N of t, it is the number of particles with the energy multiplied by t into dt. That is the energy upon number of particles with energy t, that way. And we are integrating from 0 to t0. So this is the formula for getting the average energy of the particles. Now here T0 is the endpoint energy, T is the energy, and N of t dt is the number of particles with energies between T and T plus dt. Now when a beta transmission takes place, the energy of the nucleus decreases by an amount first equal to the maximum or endpoint energy of the emitted spectrum. Okay. So thank you so